Okay, so good morning, everyone. Let's get started. In the previous class, we were looking at channel coding with cost constraints, and I proved the channel, at least the achievability part of the channel coding theorem for a channel where you have an input cost constraint. The goal was to transmit a message reliably across the channel and under the constraint that some function alpha of the summation I going from 1 through n alpha of xi should be less than or equal to beta. So this is the cost constraint, which is similar to a power constraint that one might uh, that you might have to satisfy in some particular channel. Note that if I choose alpha of xi to be xi square, then I get the regular power constraint that you have in various channels like the AWGN channel, right? And for such channels with cost constraints, the capacity is given by this quantity. It is the maximum of the mutual information between x and y. But now this maximization is taken over all input distributions which satisfy this expected cost constraint. So the maximum overall px expected value of alpha of x should be less than or equal to beta. Right. So one thing to note here, it's a subtlety, but here we don't, what we demand over here, that what we demand the code words to satisfy is that all code words should satisfy this constraint. So in some sense, this is actually a maximum power constraint. By maximum power constraint, I mean that the summation overall alpha of xi should be less than or equal to n times beta. Sometimes you also have an average power constraint, by which I mean that you don't want all the code words to satisfy this particular inequality, but on average, when you average over the randomness of the message, this constraint is satisfied. So this is sometimes called a maximum power constraint, although it's slightly different. Yeah. So this is what is called a maximum power constraint, and you can conceive of other constraints as well. So there is also the peak or the so-called intensity constraint, which says for which alpha of xi is mod xi, and so on. So you can have different different functions alphas, and the capacity is always given by this as long as the constraint is in this particular form. So it has the single letter form. So its summation alpha of xi should be less than or equal to n times beta. Now suppose that you want to satisfy multiple constraints. So let us say that you want to satisfy summation over I alpha 1 of xi should be less than or equal to n times beta 1, summation overall I alpha 2 of xi should be less than or equal to n times beta 2, and so on. Then the capacity expression remains similar, except that you want to maximize over all possible input distributions for which expectation of alpha 1 of x should be less than or equal to beta 1, expectation of alpha 2 of x should be less than or equal to beta 2, and so on. Right? So the expression looks very similar, and the proof is exactly identical to what we did. So you can basically handle any number of input constraints. And I'm mentioning this because there are many practical scenarios where you have multiple power constraints. So you can have both a standard L2 norm power constraint, and you can also have an intensity constraint. So these commonly arise when you're talking about, say, visible light communication. All right. And for all of these, the capacities are well known, and basically the expression looks very similar. All right. So in this class, I'll talk about Gaussian channels. We'll keep the discussion brief because all the techniques are essentially identical. There are some differences, and I'll highlight them as we go along. And So today we'll wrap up with the discussion on Gaussian channels, and from the next class onwards we'll start talking about multi-terminal source coding and multi-terminal channel coding. All right. So before we proceed, are there any questions? Any questions? Okay. So so our in all our discussions we have assumed an implicit assumption has always been that the input and output alphabets are finite. Right. The same thing generally holds for infinite alphabets. There's a little bit of nuance involved over there, but the techniques as is do not extend to continuous alphabet channels, and the reason is because uh, our proof technique has basically involved a typical set decoding, right? The definition of the typical set really hinges on the fact that the alphabet is finite, right? So recall that for a given distribution Px, the typical set requires you to satisfy this particular property. So mu a of, so the empirical frequency of occurrence of any symbol a should be close to the probability of occurrence of a. Now, if it's a continuous random variable, such a definition does not make sense because the alphabet itself is infinite, right? And the probability of occurrence of any particular symbol is exactly equal to zero. So let's say that you have a uniform distribution between on the interval 0 to 1. The probability of occurrence of one particular number, the probability of occurrence of say 0.5, is equal to 0 because after all, it's a continuous random variable. But the probability of occurrence that the symbol lies in some small subinterval, that is non-zero, right? So the definition of the typical set can get a bit more complicated. So there are different approaches to derive channel coding theorems for continuous alphabet channels, and I'll outline two approaches now. All right. So let's look at the power constraint AWGN channel. The channel is given as follows. So if you have n channel uses, then the received sequence yn is equal to the transmitted sequence xn plus some noise vector zn, where zn has IID components and they're all Gaussian with mean 0 and variance sigma square. Right. In addition, we want the code words to satisfy this power constraint, and typically the power constraint is in this form. The L2 norm of xn should be less than or equal to square root np, or summation I equal to 1 through n of xi square should be less than or equal to n times p. So this is our power constraint. And and before we actually even derive what the capacity is, in fact, the capacity turns out to be exactly identical to what we had in the discrete case, except that they are maximizing over all possible input PDFs, not PMFs. So the capacity is equal to the maximum of the mutual information between x and y, and this maximization is carried out over all densities on x, which satisfy this expected power constraint. All right, and and in this case, for the AWGN channel, this is maximum overall possible fx such that expectation of x square is less than or equal to p of h of y minus h of y given x which is maximum over all fx. The constraint is satisfied. H of y minus, what is h of y given x equal to?
H of j.
Correct. So it's h of z, right? And we know exactly what h of z is. It is half log 2 pi e sigma square, right? And h of y is maximized. So basically, the capacity is equal to can be obtained by maximizing h of y, which is h of z plus x, and this turns out to be maximized when you choose fx to be Gaussian with mean 0 and variance p. All right, so this capacity is simply equal to half log 2 pi e. So if we choose x to be Gaussian with mean 0 and variance p, then y will be Gaussian with mean 0 and variance p plus sigma square minus half log 2 pi e sigma square. So this is equal to the expression that you're all familiar with, which is half log 1 plus p over sigma square. All right. So this is the capacity of the AWGN channel. And one thing to note, and that is a very interesting fact, is that even if p is less than sigma square, you can actually operate at a rate, at a positive rate, right? Because let us say that p is equal to sigma square or p equal to half of sigma square, then the capacity is half log 1 plus half, which is half log 1 plus 3 over 2, strictly greater than 0. And, and that is rather surprising, right? So even though the transmit power is less than the noise power, you're still able to communicate reliably. And that is really the beauty of channel coding, right? So this is the problem. Again, we want to design good encoders and decoders for which we can which operate at rates close to capacity, and the probability of error is vanishing in it, right? So there are actually two different approaches to proving the achievability part for let's say the AWGN channel. In fact, it's a general approach which works for all continuous alphabet channels, and that approach is to just discretize the alphabet, right? So we know exactly what to do when the alphabet is finite. All that we don't know is what happens if the alphabet is infinite. So what do? You just quantize both the input and output alphabets. You know the capacity in each case, and basically what you do is you let the quantization to become finer and finer so that it tends to the actual uh, so that the rate tends to rate tends to capacity, right? So what do you do? So the channel still remains the same. It is the AWGN channel, right? Or in general, any fy given x, the input is xn, the output is yn. What you do is you quantize the input alphabet and you quantize the output alphabet. Let me call this qx and this qy. So, so what do you do? So the input, you don't transmit arbitrary real numbers, right? So let me call this x prime. This is y primes. So our effective channel is going to be this, right? So this will be our the discretized channel. Right, so this is going to be an effective discrete memoryless channel, and what you do is basically the input alphabet x prime is let us say minus j delta minus j delta minus j plus 1 delta and so on up to j delta. Okay, where I choose this delta to be 1 over square root of j. Okay, so for any positive integer j, I'll define this x prime. Let me call it xj prime for some positive integer j. Okay. Similarly, I also have a yi prime. Yi prime, which is minus I delta up to I delta, where this delta is going to be 1 over square root I. Right? So this is going to be my effective input alphabet. So when I'm designing a code, when I'm designing my code, I'm going to design so that the output, so that each code word comes from this particular alphabet. And the receiver, I actually receive a real vector, but then I map it to the closest point in yi prime. Right? So qy basically maps to closest point in yi prime. Okay, so basically I'm just doing some post processing at the receiver. So I'm first doing this processing, I'm first doing the quantization, and then I'm going to decode, assuming that the output alphabet was this. Okay, so I'm going to design this encoder and decoder to work for this particular input alphabet and this particular output alphabet. And in this case, I know exactly what the capacity is, right? So the capacity is, so let me call it Cij, right? So the capacity is equal to the maximum, so the maximum overall input distributions Px of Ix y. Right? So let me call this, maybe let me use a different notation, xjyi. xj yi, just to denote that these are quantized alphabets. Right, so I know that this is the capacity, and clearly, since I'm doing some kind of processing over here, the mutual information between this and this is obviously going to be less than or equal to the mutual information between this and this. Right, so the claim is that this is less than or equal to, so let me put it a little, so I xi, sorry, xj yi is going to be less than or equal to Ixy, the actual mutual information, the mutual information for the channel as it is, for the actual AWGN channel or for the actual continuous alphabet channel. So this is, for this the alphabet is discrete, whereas for this the alphabet is continuous. So why is this statement true?
data processing.
Exactly. So it follows from the data processing need, right? So from the data processing inequality, this is obviously going to be strictly less than the actual mutual information. So the capacity of the discretized channel is going to be less than or equal to the capacity of the actual continuous alphabet channel. But as as you let I to tend to infinity and j to tend to infinity, this actually tends to the true capacity, which is equal to the maximum overall input densities satisfying whatever constraints you have of the mutual information between x and y. Okay. So this works in general. So you actually design a code for the discretized channel, and then you know that as you, if I and j are large enough, then the rate that you can achieve will be arbitrarily close to capacity, right? And this is a valid scheme, and in fact this is exactly what is employed in practice, right? After all, when you're communicating across an AWGN channel or a fading channel, you don't transmit arbitrary real numbers, right? You transmit points from some constellation, which is effectively obtained by discretizing the input alphabet, right? And at the receiver, although in many cases you do some sort of soft decision decoding, uh, after all the receivers that you use are still digital, right? So some form of discretization is also done at the output. So although you can approach rates close to capacity, you're actually achieving the capacity, you're getting close to the capacity of this discretized channel or the quantized channel, but the quantization levels are small enough, or the rates that you're choosing or you're operating at a point where it is actually close to the capacity of the actual continuous channel. All right. Uh, any questions so far? Any questions? Okay, so one thing to note here is that when you're discretizing the channel, it's careful to see what happens to the discrete alphabet as you let I and j to tend to infinity. After all, not every quantization scheme works. So note that you have all of Rn. Right. So you have R, whatever, minus infinity to plus infinity, and you're quantizing at regular intervals. The spacing is delta, and you're going all the way up to some, let's say, j times delta from minus j times delta, right? So that is going to be your input alphabet, and your output alphabet is also the effective output alphabet is also going to be very similar, right? So as j tends to infinity, so these are the limits, right? So this is the uh, so this is the interval where the input alphabet lies, right? The support is going to be a subset of this. So the range is going to be from minus j delta to plus j delta. So, so effectively, what is this range going to be? Max x in Right? So what is the actual range going to be, or what is the maximum peak value actually going to be? So I choose delta to be 1 over square root of j, right? So this range is
Root.
basically going to be 2 root j.
Yes.
Right? Or the maximum value is going to be square root of j.
Or sir, plus 1.
Sorry?
2 root j plus 1. 1 more for 0 if we count. Like range is.
So I'm not talking about the number of levels,
Okay,
right?
okay, sir.
So the number of levels is going to be 2j plus 1.
Yes, sir. Got it.
So the number of levels is going to be 2j plus 1, but the actual range, or the maximum value of the largest symbol that you will be transmitting will be roughly will be square root of j. Right? So as j tends to infinity, this range tends to infinity. Right? So this range becomes wider and wider as you let j to tend to infinity. But what happens to the spacing between 2 points? So as j tends to infinity, delta tends to 0. Right? So in effect, as you let j to grow larger and larger, the effective range is also increasing, but at the same time, the spacing between the points is also decreasing. And really, this is a very important property that is used particularly when you look at continuous alphabet channels over the reals. All right. So I will not give a proof of the fact that this mutual information tends to this mutual information. So as let I and j tend to infinity, this mutual information tends to this continuous mutual information. I won't give a proof, but you can just go through the textbook, the network information theory textbook that has a proof. Uh, but I also want to highlight that although this is a general approach which works for any continuous alphabet channel, there's another approach which is maybe specific to the AWGN channel, but it gives you more intuition as to what is actually happening. There's a lot more geometric interpretation that you can have if you look at it directly rather than go through this approach of discretizing and so on. All right. So the second approach to proving a channel coding theorem for the AWGN channel is the following. You start from scratch. Okay, you try to mimic what you did for discrete memory-less channels, but will deviate slightly. Okay. So similarly, just as we did for the discrete memory-less channels, we'll choose a random code book. So you'll generate 2 to the NR code words, or whatever, 2 to the AN code words, where each component is xi of j is going to be IID distributed, Gaussian distributed with mean 0 and variance p. Okay, so this is how you generate a code book. You generate a particular code book, and then this is shared between the transmitter and the receiver. And the decoder, now instead of using a typical set decoder, will use a bounded distance decoder. Okay, and the bound we are going to use is, so the decoding radius rho, this is going to be equal to square root n sigma square into some 1 plus epsilon. Okay, for some positive epsilon greater than 0. All right, so this is going to be the decoding radius, which means that if the received sequence, so you receive a particular yn, you draw a ball of radius rho around it. If there is a unique code word in this particular ball, then you declare that as the transmitted code word. If there is no code word, or if there are multiple code words, then you declare that you basically declare an error. All right. So that is how the bounded distance decoder operates. All right. So, so once again, you can mimic all the steps of the proof. There will be three sources of error. One is that the actual generated code word does not satisfy the power constraint. It exceeds the power constraint. The second source of error is that xn and yn are not jointly typical. So in other words, the received sequence is far away from the transmitted sequence. And the third source of error is that there are other wrong code words which lie close to the received code word, to the received sequence. All right, so the errors, the first source of error is that the message does not satisfy the power constraint. So this is strictly greater than n times p. But you know that the probability of this happening is vanishingly small, and we'll see that in just a bit. So the second source of error is that the distance.
Sir?
Yes.
Like, why the first event becomes error? Like, this is
I'm sorry, I can't hear. I can't hear you. It's very noisy.
okay. Can you hear me now, sir?
Yeah. So if you speak a little slowly, I think I can make out.
Okay. So what I'm saying is, why the first point with an error, like it happened for the exit case also inside. Like, why the first is like where the code work
Okay.
doesn't satisfy.
So right. So the question is, why is the first event, that is the transmitted code word, not satisfying the power constraints, considered an error event, right?
Correct.
Right. So the thing is, we want every code word to satisfy the power constraint, right? But since we're generating the code words randomly, it is possible that some code words do not satisfy the power constraint. There's some small probability of that happening, right? Now what happens? So suppose we want to transmit a message, and the code word that was generated for that particular message does not satisfy the power constraint. Then obviously we cannot transmit that particular code word. So we just transmit something else, or we just transmit maybe the all zero sequence or something like that. Right? So that is why we treat that as an error event.
Okay.
It's only because we are not allowed to transmit any sequence across the channel which does not satisfy the power constraint.
Okay.
So that is why we consider this as an error event, and that is why we just handle this.
Okay.
Okay. So the second source of error is that you look at the received sequence, the actual transmitted sequence, let's say the first message, lies far away from the received sequence, right? So the actual transmitted code word lies at a distance greater than rho from the received sequence. Right? So this is essentially similar to saying that xn of 1 and yn are not jointly typical. They're not jointly typical. So the third error event is that some other sequence, some other code word, xn of j, is less than or equal to rho for some j not equal to 1. Right? Which is essentially identical to saying that some other j, so some other code word, is jointly typical with respect to the received sequence. Right? And basically all of these can be handled in a very similar fashion. And to prove this, basically what we need is are two tools. So previously we used Chernoff bound to bound this probability and parts of these two probabilities, and the second was joint locality. Right. So now we have something a little more geometric. One is, of course, a bound on the volume of a ball, and the second is something similar to Chernoff bound. All right. So again, I won't give proofs of these statements. You can look it up online. Here's also a reference to the second statement over here. So the first statement is basically a bound on the volume of a ball of radius r. So it's an n-dimensional ball of radius r. The volume of this ball is given by this particular quantity, and this turns out to be approximately equal to, this is roughly equal to 2 pi e raised to n by 2 times r by square root of n raised to n times 1 plus, so times some quantity which is polynomial in n. I can just say that this is 1 plus little o of 1. All right, so this is what the volume of a ball of radius r is equal to. And the second tool that is needed is something similar to the Chernoff bound. It says that if you generate xn IID drawn according to a Gaussian with mean mu n and variance alpha, so it's okay. So it's not exactly IID perhaps, but the mean is some vector mu n, and you have a covariance matrix which is alpha times the identity. So all the components have the same variance. Then the probability that the distance between, or the square distance between xn and mu n is not close to alpha, this vanishes exponentially in n. So what this basically says is that if I draw a Gaussian with if I generate a random Gaussian vector with mean mu n and variance alpha, then basically with very high probability, with probability 1 minus something which is exponentially decaying in n, xn is going to lie in some thin shell. So the norm or the distance between xn and mu n is going to be between alpha times 1 minus epsilon, 1 minus delta, and alpha times 1 plus delta. Alpha, and this gap is going to be root alpha to root delta, roughly. Okay, so this is what this geometrically says, and you can prove this formally. Here's a reference of the proof, and this statement, and both these statements are good to know in general. These bounds are very useful in not just information theory but also statistics and machine learning. All right, and probably one interesting fact about the volume of the ball is the following. So let us look at the volume of a ball of radius square root np. Okay, so as I said, this is roughly equal to 2 pi e raised to n by 2 times this, right? So this is, if you ignore the lower order terms, then this is equal to 2 pi e raised to n by 2 square root np divided by square root n whole raised to n, right? Which is basically 2 pi e p raised to the n by 2. Right? So this turns out to be the volume of a ball roughly equal to the volume of a ball of radius square root np. Okay, but what is this equal to? So this is, if I can write this in a slightly different way. Let me write it as 2 raised to something. Okay, so I write it as 2 raised to n by 2 times log of 2 pi EP. Right? I've done nothing else except saying that 2 pi EP is equal to 2 to the log 2 pi EP. That is it. All right. So is this something that you recognize? Have you seen this? What does this look like?
It is the entropy of the input.
Correct. So it's basically equal to 2 raised to n times the entropy of a Gaussian random variable with variance p. Right? And that is exactly, that is really the geometric interpretation of this. So if you take a Gaussian, so if you have a random variable which is uniformly distributed in this ball of radius square root np, then the entropy will basically be equal to half log, roughly equal to half log 2 pi EP. And even if you take a Gaussian with variance p, then the entropy will again be half log 2 pi EP. So for very large dimensions, a Gaussian behaves in this particular fashion, that it is roughly uniformly distributed in a ball of radius roughly equal to the variance. Okay, and just by using these facts, you can prove each of these. So now, as soon as you have this inequality, just using this inequality, you can prove this statement. So the probability that this happens, the probability that the generated code word does not satisfy the power constraint, this is basically again exponentially decaying in n. Similarly, given the transmitted code word xn of 1, the received sequence is basically xn of 1 plus AWGN, Gaussian noise, and you know that the probability that this does not lie within a distance of square root n sigma square roughly is again, that is also exponentially decaying in n. So this probability of error is also vanishing in n. And similarly, you can show that this probability is also vanishing in n. So given any yn, the probability that some other xn of j lies within distance rho of this is also exponentially decaying in n. For this, you will need the volume of the ball because xn of j, so the probability that xn of j lies within a ball of radius square root n rho to yn, that is given by roughly the volume of the ball divided by the probability of xn, yeah, you'll have to compute that separately. So in a very similar fashion, just identical to what you did for the discrete case, you can just compute each of these probabilities and show that all of them decay exponentially in n. So the overall probability of error also decays exponentially in n as long as the rate is less than half log 1 plus p over sigma square. Okay, so I'm not doing this in too much detail, but what is important is the approach or the ideas involved rather than the exact calculations themselves, because the calculations are similar to what we have already done previously. Okay, are there any questions?
Sir, you are not audible. You are on mute.
Yeah, thanks for letting me know. Right, so now that we've seen the capacity of the point-to-point AWGN channel, let us see a slightly more complicated setup where the transmitter and receiver are not connected by a single point-to-point AWGN channel, but rather there are multiple AWGN channels. Okay, and this, for example, this is a very common occurrence when you have something like an OFDM system, right? You have multiple subcarriers over which you can transmit, and 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 for each subcarrier you see an AWGN channel, but these are not identical AWGN channels. The capacities or the noise variances or the channel coefficients could be different across each of these channels. Okay, so suppose that you have D parallel channels from the input to the output. Okay, and the ith, so let's say the first channel is basically the following. So y1n equal to h1 xn plus z1n, y2n equal to h2 x2n plus z2n, and so on. Ydn is equal to hd xdn plus zdn, where all the zi's are IID, Gaussian with a mean 0 and variance 1. And the coefficients h1, h2, h3 up to ht, these are all some known coefficients. They're all different. They could be different. They could be the same. It doesn't matter. But we're going to assume that these channel coefficients HIs are known both to the transmitter and the receiver. HT known to both the transmitter and the receiver. Okay, and so basically, what is the setup? The setup is that the transmitter can send D. So there are D parallel subchannels, and you can transmit a code word in each of these subchannels, right? And the receiver sees D vectors, right? And jointly decodes these D vectors to the actual message. So you have a message W, you have an encoder. The encoder now outputs D code words. The code book used for each of these subchannel could be different. So this is x1n, x2n, xdn. So this goes through the channel, and with the output of the channel you see y1n, y2n up to ydn. The decoder sees all of these, the outputs of all of these D subchannels, and outputs an estimate W hat. Right, so the goal is again the same. We want to transmit a message. This is a binary sequence of length kn. reliably. So you want to minimize the probability of error. At the same time, you want to ensure that the rate is as large as possible. The input should satisfy a joint power constraint. So you have a total power budget of n times p, and you can distribute this power across the various subchannels. All right. So maybe you can allocate more power to the first subchannel, less power to the second subchannel, and so on. But you have a total power budget to satisfy. Okay, and so the goal is to find out what the capacity of this channel is. Right? So you know that if it's a single AWGN channel, then the capacity is half log 1 plus p over sigma square, or in this case, for the ith subchannel, the capacity is going to be half log 1 plus hi square pi, where pi is the amount of power allocated to subchannel I. Right? So the total rate at which you can transmit will be the sum of the rates over which you can transmit across all the subchannels. All right. So is this setup clear? Is the problem statement clear? Or are there any questions? Okay, so the capacity is given by this sum rate, the sum of the capacities of the individual subchannels, and therefore, so this is for a particular power allocation for one particular power allocation. Less than or equal to P. So the capacity is really, this is for one particular power allocation. So the capacity is the maximum over all possible power allocations which satisfy this power constraint of the summation I going from 1 through D half log 1 plus hi square pi. Okay, so you can use Lagrange multipliers and solve this. I'm not going to do it exactly because we've already done it in the channel coding class. So you can try to solve this optimization problem on your own by introducing Lagrange multipliers to satisfy this particular constraint. PD less than or equal to P. Right, and basically the solution turns out to have the following form. So pi star will be equal to some lambda minus pi hi square. All right, so this has the following interpretation. So if hi square, so it has the following water filling kind of interpretation, where if hi is, so obviously, I mean, intuitively what this says is that if the channel coefficient hi is large, then you should be transmitting at a higher rate across that particular subchannel, right? Because you have a better subchannel, you can transmit at a higher rate across that particular subchannel. If you have a worse subchannel, then you can then you should be transmitting at a slightly lower rate across that subchannel. But how do you decide how much of power to allocate to each subchannel? It turns out that you can have the following argument. So you have a total power budget of let's say whatever. So you have, this turns out to be similar to setting a threshold lambda, and then looking at the difference between 1 over hi square and lambda. Okay, so the total amount of power that you want to allocate to each subchannel, to the ith subchannel, is equal to this basic uh, the amount left over. So it's like filling water. You have these levels, okay, and this is the maximum water level that you can satisfy, that you can fill in, and basically you pour in uh, power in some sense. It's like filling in water into each of these levels so that the overall level is fixed at lambda. Okay, and so basically you will allot more power to this particular subchannel. The highest power will be allotted to this particular subchannel, and slightly less power to this, and less power to this. If 1 over hi square is very large, or basically if hi square is too small, then you will not allocate any power to that subchannel at all. All right, so this is commonly called the water filling argument. The water filling solution, or the water filling argument, and this arises in any such optimization problem where you want to maximize the summation of some quantity like half log 1 plus alpha I pi, where you want the pi's to satisfy a total power constraint less than or equal to p. All right, so you can take a look at the Cover-Thomas textbook. So you can either section 9.4 of Cover and Thomas, or section 3.4.3 of the El Gamal and Kim textbook, and just quickly go through the proof. All right, so we'll discuss Gaussian channels once again later on, once we've discussed a little bit of multiple access channels, but henceforth we'll only focus on the discrete alphabet. All right. Any questions? Any questions? Okay, so if not, we'll meet in the next class.